Dylan's going to stick around for a minute, and we're going to talk about wellbore storage. You told me you had a hard time with the Laplace transform. That'll be on the exam, right? Okay, so how would you characterize the discussion of wellbore storage? You have to start with a picture. We discussed all this, correct? Okay, so I started to write water, but let me make gas since that's more compressible. But the whole wellbore is full of a compressible liquid. In this case, we'll call it, what's a good name? Spongy. It'll have its own name. It'll be spongy liquid. All right, so, and the reason it's not gas is because gas has some other issues. What's spongy liquid mean? That the compressibility is constant. Now this one's easy to understand. Now gas, of course, the compressibility is not constant. The other one is where we have a liquid level in the well. I know I'm covering up the rod, sorry about that. And this liquid level changes as a function of pumping. Obviously, if you're pumping, it goes down. If you're shut in, it goes up. We have a well across the street where we can demonstrate this very well. Unfortunately, through a system of former Soviet-like bureaucratic things, we cannot seem to get the electricity reconnected to the pump. Sorry, ladies, I didn't mean to, suggest anything was wrong with the former Soviet system. Our newly independent brothers and sisters are welcome to the economic meltdown. We're depending on you to spend us out of it. But we'll try to get the pumping unit ready before the end of the semester. Basically, it had to be moved in order for some construction. It's been put back into place. The power needs to be connected, and then the company comes back out and runs diagnostics on it and will tell us. But it is more or less identical to the configuration that you see here. This is our Texas A&M water well, and we should be able to run a test on this. There is a slight problem with it, but it has to do with the electronics. Hopefully that'll get fixed and we'll be on our way. All right, so the way this is going to work, let's stay with the easy one. The easy one is kind of the conceptual equation of where we have the sand phase flow rate minus the rate, the formation volume factor, which of course is constant, and the number 24. Why is 24 there? Time for well testing is always in hours, okay? That's important to remember. What's rate in? It's in something per day, so we have to have a conversion factor. All right, Marmina, you ready? dPWF, dPTF, dt. There's a minus sign. dPWF, dt. Now we're measuring the pressure where this is PWF down here, and this is PTF up here. Do we need to measure PTF? Why are you winking at me again? I thought you got the message. Why are we measuring PTF, the surface pressure? If you were going to make an assumption at this point, what would you assume about the surface pressure? Is it fair to assume the surface pressure is 0? I see some heads doing this. I don't see any heads doing this. Mr. Stone, it should not be 0, so that is out, okay? Anybody else have any suggestions for PTF? Okay, if PTF is equal to a constant, what happens? Then this goes to 0. Convenient, right? Okay. Now, whether or not this is true kind of makes things a little crazy. Did you mention that some really weird things can happen? Like what happens if gas bubbles start coming up? Now, the pressure in the gas bubble is, let's say, PWF, right? And the gas bubble comes up to the top and it can't expand. What's the pressure when it gets to the top? PWF. So what's the pressure downhole now? It's PWF plus at the top plus the hydrostatic. And there's an old example where that could be 10,000 psi. If this is 5,000 psi and the well's 10,000 feet deep, we add this, take it upstairs, it's 5,000, pushing on 10,000 feet. So what happens is at the bottom, you get 5,000 plus the hydrostatic. Why is this important? What's the pressure profile going to do? If you're looking at the bottom hole pressure profile and you shut in the well, what do you think is going to happen? It's going to go up and there'll be a big hump, and then it'll come back down and take another trend. This is that bubble rise. There's a lot of names for this. It's called phase segregation and some other things, and maybe I've overemphasized this. Let's say it's more like this, okay? What else could happen? You could burst the casing, right? Theoretically, at the bottom. If you have 5,000 psi rise to the top and then another 5,000 psi added onto that, if it exceeds the casing rating, it could burst it. I don't know of any cases like that happening. But this bubble rise thing will drive you insane because there's nothing like it. We need to get an example and show them. It happened a lot in the good old days, right? So we'll have to show them an example of that. Again, way beyond the scope of today's discussion. I just wanted you to be aware of it. All right? So we've assumed that PTF is constant, life is good. What else can we do? How many of you know how to draw these graphs? What's the rate profile, the sand face rate profile going to be? What's the well pressure going to be? Well, here the initial pressure is PI, and here the surface rate is Q, right? So what happens at the sand face? Well, when I open this well right here, what's going to happen to the sand face rate? Eeny, meeny, miny, mo. Is it going to be the same as the surface rate? Yes or no? If you say yes, then you will be in this class next semester, you see. So why don't you say, no, it ain't, and then tell me whatever. Where would you like it to be? It starts here. The rate influx here is approximately 0 at t equals 0, right? Okay, so then it comes up and it makes a lazy S shape. That's wellbore storage, boys and girls. So, Miss Lever, are you up to participating today? No, you don't feel good. Looks like that burrito's about to come out. You okay? No? You don't want to play? Where's Loco? Is he awake? Hey, how's it going back there? Did you forget to shave again this month? It is the 9th. All right. So here, Loco, here's the rate profile. What's the pressure profile going to do? If there's no rate, if there's no rate as a function of time, what happens to the pressure? I'll give you a hint. Stays constant. Very good. But it's not exactly constant. It's going to drop a little bit, right? And then, I don't know, it does something like that, okay? I'm thinking in logarithmic terms. Sorry, I forgot to label my graphs. What happens if you don't label your graphs? 0, very good. I feel the love, okay? So, the assumption that we can make here is what? That QSF is approximately 0. Is that okay? So, QSF is approximately 0 where? At t equals 0. So, in that vicinity. You think that's enough? I think that's enough. So then what you need to do is you need to solve for the pressure change as a function of time. You might want to be thinking about this soon. Okay? Now, let's move on to the next part of the discussion. Come on, you stupid machine. What'd I do, make it crazy? Was there something on the previous? Oh, you drew it by hand. Thank you. All right, and as we just pointed out, if the rate, the sand face rate, is basically 0, what's going to happen to the pressure? So this is the result of the integration of that previous discussion. And there's a mirror image. Now, the problem with wellbore storage is there's absolutely nothing we can do to eliminate it completely. So, if it's a tax that we have to pay, let's see if there's something useful that we can get out of it. The slope of this line is M wellbore storage. That's this term right here. M wellbore storage. Are there any reservoir properties in the M wellbore storage term? Is the number 24 a reservoir property? No. Is the rate a reservoir property? Well, not exactly. Is the formation volume factor a reservoir property? No. Is the so-called wellbore storage coefficient a reservoir property? Class? No. It pertains to the wellbore, hence the name wellbore storage coefficient. So all we can do with the slope is validate the wellbore volume. That's what we could do. We won't because it's a stupid thing to do. What about this PI thingy? That is a reservoir property. So by extrapolation, we can determine the initial pressure. Now, all of you who are sitting out there thinking, every time I look at a data set, somebody's going to tell me what the initial pressure is. You better wake up and smell the roses. I've had 2 cases over the weekend, one from Malaysia, one from my El Cheapo buddy in South Texas, send me some production data and ask me to look at them, and let's talk about what wasn't in there. There was no initial pressure. There was no well completion data. Had to ask them both for that. There was no porosity, permeability, thickness data given. Had to ask for that. There was no fluid property data given. They had to guess that. The guy in Malaysia had over 100,000 data points for the rate and the pressure before he realized, in comparing the 100,000 data points from the rate taken every few seconds on a Venturi meter to the rate that was proven means shot over to a tank through a separator, which is correct, that there was a substantial difference in those rates. And so he went back and tried to correct the rates. He didn't do a very good job. The pressures, on the other hand, were outstanding. They were measured bottom hole pressures, continuously measured. Whenever the pressure data tells you that the well is shut in, and the rate data tells you it doesn't know because there's a gap, that's a bad sign. Something that even the most imaginative of you, you're not going to be able to analyze around. You're going to see a lot of continuously measured rate and pressure data. Make sure you do some QC. You looked at the quality control. You looked at the data that I showed you from South Texas. What did you think of that?
Garbage.
Well, I think you're being polite. The pressure data taken on a daily basis did what? Remember? It drew down, whatever this junk was, and then it popped back up, and each time it came to this, they produced it some more. It was jumping all over the place, right? And then they shut it in again, and it popped back up. And it always kept popping back up to the same position. There was, again, some more junk. Junk, in this case, is called production data. It's not supposed to be junk, but as I mentioned, he's an El Cheapo. So if the formation comes back to the same pressure each time, what's your gut instinct? This is probably the right pressure, okay? But this morning he sends me an email. He didn't even look at the data, and he said this was 1,040 psi. This, of course, was 1,040, and this was 1,040. And he goes, that's the highest pressure we've ever had. Scratch head, scratch bottom, say good luck. And the rates, what do they look like? You don't want to know. How would you feel, Marmina, if you owned a well that made 24,000 cubic feet a day?
I'd buy you dinner.
You'd buy me dinner. And then what? You try to sell me this well? 24 MCF a day.
No.
Not million.
Sorry.
24,000. How much money would that be? This is not the highest rate the well ever made, but it's pretty close. You're going to deal a lot with small companies, trust me. And they want a miracle. All right, how do you guys feel about this? Somebody say, bring it on. Where's my Russian friend? You like the Laplace transform, right? You forgot the Laplace transform? Ms. Fletcher, how do you feel about it? Sorry, you're indifferent? You're indifferent to the Laplace transform? This has made possible all of the things we do in modern reservoir engineering, and you're indifferent. They're going to walk out of here and be paid more than me and a lot more than you. And and they don't care. If you gave her the Laplace transform, you'd probably say, oh, look, I can make a butterfly or a flower. You're indifferent. Who's not indifferent to the Laplace transform? Who feels the love for the Laplace transform? Who wants to use the Laplace transform? Mr. Zanero, you want to use the Laplace transform?
Bring it on!
All right. I think we can add a problem to the exam. Why did we write this formulation? Y'all be quiet. You know I'm not going to do that. All right. This is in the Laplace domain. And what it's telling you is that there's a relationship. Did Dilhan explain this carefully to you? This is the wellbore, and this is the reservoir. I didn't really write out the other word, This is a reservoir solution, and this is the wellbore solution. What does this equation tell you? May I turn the lights down so you can go to sleep while you're thinking about this? Mr. Perry, I can always rely on you for a mature and incorrect answer. Are you ready? What does this tell you? There's some weird capacitor type rule. Is that what, who's an electrical engineer in here? Anybody? Used to be, flunked out, that sort of thing. So what happens is, if we write this thing out a little differently, did you play this game with them? No? You think they enjoy it? So we take 1 over PWD, we're going to forget about the nomenclature, is equal to 1 over PSD plus this Laplace transform squared thingy CD. Okay? Mr. Perry, so there's some sort of weird capacitance rule, right? This is a reciprocal of what we measure, or what the resultant solution is. This is a reciprocal of the known solution for the reservoir, and this is the solution for the wellbore. It's actually the reciprocal of that, but it's the reciprocal of the, at any rate. Did you ever explain it to anybody this way? But it's kind of cool, right? So we're adding up the effects of these, and where do we have to do it, Mr. Zanero? In the Laplace domain. So this is actually the reciprocal of the variable rate solution. It's a general problem. This is the constant rate. And this is the wellbore storage part. Or this is the wellbore part, I should say. So what we did is we used mathematics to add these together. Think very carefully, class. At early times, the only thing that's participating in this well test is what? Stop winking at me, Marmina. I want to file a restraining order on you. Ladies? Huh? You just got something in your eye? Yeah, okay. Freak. All right, so we have the wellbore. That's the conduit to the reservoir. When we first turn the well on, what happens? All the action is where? In the wellbore. So that term over here on the right, that controls everything. And then later on, what happens, Ms. Fletcher? The wellbore component kind of diminishes, and the reservoir starts to dominate. But there's an interface where neither of them make a lot of sense, and that's an averaging formula that explains that. But eventually, that PSD term will dominate the wellbore term, and we will have the full solution, or this is the full solution. Now, it's kind of hard to explain in the Laplace domain, and I'm glad Dilhan did it and not me. Is everybody ready? Okay, here's what it looks like. And you explain this in excruciating detail, right? No? Ooh, Wally left us some lunch. Maybe not. Okay. Wally, you ready? All right. So if it's wellbore storage only, what's the equation for that? Wellbore storage? Yeah. Let's go back, right? Here's the equation. I got to write it down. What is it again? Let's do PI minus PWF, right? And that's equal to what? QB 24CS times T. You like that? That's wellbore storage only, right? So let's go forward 2 slides. Why did I do that? I don't know why, but I obviously wanted to. All right, let's write this equation down. So delta P is equal to QB over 24 CS times T, right? Now when we write this in dimensionless form, do you know what it's going to look like? If you get this right, I'll let you take one gut punch to old Marmina here, and I'll hold him. You get it wrong, you got to wear Marmina's uniform for a week, inside out. What's the punishment going to be? Don't you outrank him? Not really. You don't really care? Okay, well then we'll come to you. What's the dimensionless form of this going to look like? I'll give you a hint. You ready? What happens when EXP is approaching a really small number? Okay. So what do you think is going to happen? Okay. What happens when it's a really big number? Okay. But it's negative. Okay. It's going to be PD is equal to, or actually I guess we should write it this way. PWCD is going to be equal to TD over CD. Okay? Do you see that somewhere here? Sorry? So how does this work? If this is small enough, then this exponential becomes 1 plus epsilon, right? And then what happens? 1 minus 1 plus, it's actually 1 minus epsilon. Like that, right? And epsilon is equal to what? TD over PD CD, right? So then what happens? That 1 cancels with that, right? This PSD cancels with that. And this becomes what? TD over CD. Pretty clever, huh? It's an approximation, but it gives us the right form. So do you see TD over CD on this graph? Oh, for crying out loud. Suddenly you awake. The negative cancels. Don't worry. Speak louder. Everybody's trying to listen. Does anybody see this on the graph? Sorry? Someone else? Where? Somebody got a triangle? Here, I'll just use this. Is this your little gray book? Full of love poems? There it is. Tell me when the quiz needs to be handed out, Don. Okay? Now this equation tells us something else. Wally, you were saying, when TD gets big, what's going to happen? This term goes to 0, right? And then what happens? It's equal to, so this is the reservoir. And this is the wellbore. Where's the reservoir only curves? The far right-hand side. All of these are the reservoir curves. Right? So, what happens in between? Anybody? This is well plus reservoir. And tell me that again. But this is the distortion part, right? We have no clear signal. We cannot interpret the reservoir or the wellbore. Over here, it's definitely wellbore only. Over here, it's definitely reservoir only. How do I know that I can't tell the difference between reservoir and wellbore in the transition or in the distortion region? Sorry? They're not constant. They just look constant. They're logarithmic. We need to make a semi-log version of this. People would understand that better. These actually are semi-logarithmic. The PD is equal to some constant A plus B natural log of T, D, over here. That's what that is. But what about inside of here? Look at the shapes, people. Somebody tell me something about the shapes. Okay, here's the weird part, right? We stop having the exam. This is where the interpretation part of the course begins. We're trying to use math and science to explain what you're going to see and why you're going to see it. The first part of the course is all about just beating up on you with the math. Now we're going to actually apply it. Do these trends all look the same? Yes. Therefore, there is nothing unique about it. If Mr. Ilk comes in and matches his data set here, and then I take it and I move it up to here, there's no difference. Or if you take it and move it down to here, there's no difference. This is what's called a non-uniqueness. Something cannot be more unique or less unique. It can only be unique or not. So this is a non-uniqueness. Your data could fit anywhere on here if we were doing a data fit. So what has to happen in order for us to sample the reservoir properties? It's about time. You got to get enough what? Time. Everything to the right of this is probably okay. Everything to the left of this, forget it. You're learning a very valuable lesson today. What's that lesson, Marmina? That God has conspired with the wellbore to make your life miserable. Okay? How do we reduce this effect, class? If we reduce the wellbore storage component, in theory, we can reduce its effect. Bill Hunt, comments? Can we reverse solve this problem and remove wellbore storage? In theory. You have a dissertation that says that? And I have a dissertation that says that. But in practical terms, no. All right. Everybody ready for their quiz? Everything up except your pencil.